less confusing if we choose a different... This might be a little bit of sleight of hand that we're doing here. I don't think that this is relevant, actually. Oh, did we miss this? No. Well, I mean, maybe, but not here. Let's see. I'm finding this quite difficult to read. We can rewrite it. Right. Though then we are going to have to turn the page again. In the midst of this proof, which is a little bit disruptive. Let's confirm that we have transcribed this correctly. Yeah, okay. From the left-hand side, R is a relation is defined to be interderivable with the expression for all D. If D is an element of R, then there exists a P such that D is, there exists a P and there exists a Q. Such that D is equal to the ordered pair PQ. Okay. Which is interderivable with the expression there exists a P and there exists a Q such that D is equal to the ordered pair PQ, or D is an element of R. Okay, and now from the right-hand side, for all E, E is an element of the identity of, okay, the identity of the domain of R /R, then E R. Okay. And if E is an element of R, then E is an element of the identity of the domain of R slash R. Okay. So, interderivable with the expression not, I'll have to go ahead and perform the conditional equivalence, not there exists a P and there exists a Q and there exists an R. We could start on different letters. STU. Actually, we didn't use R up here. RST, then UVW. There exists a R, there exists an S, and there exists a T. Okay. Such that E is equal to the ordered pair RS and the ordered pair RT is an element of the identity of the domain of R. And the ordered pair TS is an element of R. Okay. We're going to cheat a little bit there, or E is an element of R. Okay. And there exists a U, and there exists a V, and there exists a W. Such that E is equal to the ordered pair UV, and the ordered pair UW is an element of the identity of the domain of R. No. Yes. And the ordered pair WV is an element of R. Okay, or not. E is an element of R. Okay. Which is interderivable with the expression. We could have a term for, we could have a color for negation. I guess we'll recognize that we've distributed this. Mathematics is limited primarily by the width of paper. I could get out a sketchbook. We could do all this in a sketchbook instead. Have page out to here. Or alternatively, we could flip like this and just go across the midpoint boundary. Interesting idea. Let's see. Alright, so not E is equal to the ordered pair RS, or not the ordered pair RT is an element of the identity of the domain of R. Yeah, whatever. Or not the ordered pair TS is an element of R, or E is an element of R, and E is equal to the ordered pair UV, and the ordered pair, that should be no, yeah, that's right. The ordered pair UW is an element of the identity of the domain of R, or the ordered pair, the ordered pair WV is an element of R. That should be an AND. Not E is an element of R. Or not E is an element of R. Okay. Actually, if I understand this right, this is a mistake. This should be not D as an element of R up here. If I understand this right, well, if we want to get back to exactly the same position we got to last time, what horrible trick did we perform last time? So we observed that from this term, not D as an element of R, for all D, not D as an element of R. Yeah, I'm not, maybe that quantification, maybe I'm doing something tricky there that I shouldn't be doing. But the idea was that if we have the quantification for all D, not D as an element of R, then we could say and. We could and on to this or express, or to this disjunct, the term not let me see. Actually, we have to unfold this further. The point is that we get one of the disjuncts that we, well, okay, hold on. Let me think here. well, we can go back and look at it. It's not cheating. So we distributed this term through via the AND into this collection of disjuncts, and then we immediately ANDed down this term and this term, and then this term. I don't remember what this dirty trick was. So if I distribute this term, which is the entire line, through this collection of disjuncts, I get this and the line, this and the line, this and the line. And then when I distribute through on that and, we get this term and, so say P and Q or R, so P and Q or P and R. And then we ANDed down. Alright, I think we're gonna have to do this again to make sure this wasn't hand waving. Okay, let's see. Well, first we need to expand these identity of the domain of R terms. So let's do a quick lemma here. For all D is an element of the identity of the domain of R, is interderivable with the expression there exists a P such that D is equal to the ordered pair P. And P is an element of the domain of R. Okay, which is interderivable with the expression there exists a P such that D is equal to the ordered pair PP. Exists a Q such that the ordered pair PQ is an element of R. Okay. All right. And what does that give us? So interderivable with the expression not E is equal to the ordered pair RS, or not right, so another lemma that we established earlier, if we have an expression like this, the ordered pair RT as an element of I, we get that R equals T. Okay, or I don't know, that raises an interesting point though. That interesting point being that if I give myself that term, yeah, I don't know what to think about that. The idea would be, if I said the ordered pair RT is an element of the identity of the domain of R and R equals T, and then I pass the negation through. But the idea would be that we generate the term R equals T, we use it to rewrite, and then we delete it without dropping the interderivability assertion. And then it's not there to be negated. But now that feels kind of ad hoc, which I don't like. Like, that isn't a problem here. I mean, because these are all ANDed together. But then actually, these are all ORed together. So I don't have R equals T and T equals S to get the transitive switch on all of these ordered pairs. Did I take advantage of that over here? Erroneously? Yes, I did. Huh. Does that matter? I mean, it might matter for pattern matching, but as it were, how do we communicate the fact that R is equal to T to this? And then for that matter, we never had that T is equal to S. Huh. So maybe I made more mistakes during this proof than I thought. Not E equals the ordered pair RS, or let's see. Not there exists a I guess this would need to be T, but we've already used T. So I guess this would need to be Q, but we've already used Q. No, we didn't use Q, we used it for the lemma. Alright, so there exists a Q such that D is equal to the... Oh, wait a minute, hold on. Right, well, it's not D, it's specifically this element. The ordered pair RT is equal to the ordered pair QQ. And the ordered pair RT. I'm not following. What am I saying here? I'm confused. We're trying to make some pattern matching happen between these two lines, and I'm not succeeding at it. Right, well, I think we have to, yeah, I don't know, this is confusing. Well, and the problem is that we have to choose one of... We don't have to choose here. No, it would be Q is an element of the domain of R, not either R or T. Okay, so it'd be Q... and then there would exist an N, I guess, such that the ordered pair Qn... No, NQ is an element of R. We could just do Pn. PQ. Out of it. There exists a P such that the ordered pair... This would be QP, actually. So this is the first term, and then we have or the negation of the ordered pair RT is an element of the identity of the domain of R. And we're saying that... So we say D, which in this case is the ordered pair RT, is an element of the identity of the domain of R, is interderivable with the expression there exists a P such that D equals the order pair PP. Hence, there exists a Q. Yeah, we could use better letter management. Maybe we just start at A. And yeah, it seemed the requirement that we only use the latter half of the alphabet is an unwieldy requirement, especially considering that we never, or so rarely, designate individuals. We rarely step down from saying that for all P to Q, like for all P, yeah. For all S, P, the proposition holds, we rarely step from a universal quantification to an individual quantification, which would be the justification for reserving the first half of the alphabet. But we often run into these annoying, skin-crawling slowdowns due to overuse of variables. Let's see. Alright, so there exists a P such that the... Okay, so how did we get here? We said there exists a P such that D is equal to the ordered pair PP, which became there exists a Q such that the ordered pair RT is equal to the ordered pair QQ. And then we would have the follow-up, and Q is an element of the domain of R, which would necessitate, or which then necessitates the next quantification of P, confusingly Q up here. There exists a P such that the ordered pair PQ is an element of R, which confusingly becomes the ordered pair QP is an element of R down here. And then we have or not the ordered pair TS is an element of R, or not E is an element of R. I think we're going to start over again, or at least start over the right-hand side with this new rule. Alright. And then we're going to have and. E is equal to the ordered pair UV. And there exists an A such that the ordered pair UW is equal to the ordered pair AA, and there exists a B such that the ordered pair AB is an element of R. That should not be closed. Okay, and the ordered pair WV is an element of R. Or not E is an element of R. Alright, let's start over on the right-hand side. for all E, E is an element of the identity of the domain of R/R, then E is an element of R, and if E is an element of R, then E is an element of the identity of the domain of R/R. Okay. Sure. Okay, so that will become this is interderivable with the expression for all A, for all B, and for all C. Rather, there exists an A. Well, okay, we can immediately distribute, I suppose. All right. So we're already distributing the negation from taking the conditional equivalence. For all A, for all B, and for all C, not the ordered pair, not E is equal to the ordered pair AB, or not the ordered pair AC is an element of the identity of the domain of R, or not the ordered pair CB is an element of R, or E is an element of R. Okay. And there exists a D, and there actually we already know now we have a template, though this might be a confusing way of doing things. Yeah, I think we probably have to get used to jumping letters, because we can avoid jumping letters now by allocating in advance D and E. I think D and E. Yeah, both D and E, because we have to bind two additional letters in deconstructing the D as an element of the identity of the D of R, domain of R. Okay. But we only know that in advance because we've already performed the deconstruction, whereas on future constructions we will not have already performed the deconstruction. So I'm just going to get used to having to jump letters. Alright, so there exists a D, there exists an E, there exists an F, such that E is equal to the ordered pair DE, and the ordered pair DF is an element of the identity of the domain of R, and the ordered pair FE is an element of R. Okay, or not E is an element of R. Okay. This is interderivable with the expression So there exists a G such that the ordered pair AC is equal to the ordered pair GG, and there exists an H such that the ordered pair GH is an element of R. Okay. Or not the ordered pair CB is an element of R. Or E is an element of R. Okay. And E is equal to the ordered pair DE, and there exists an I such that the ordered pair DI is nope, rather such that the ordered pair DF is equal to the ordered pair II, and there exists a J such that the ordered pair IJ is an element of R. Okay. And the ordered pair FE is an element of R. Or not E is an element of R. So even if I replace the ordered pair AC with AA, there's one point that we have AC and then we have CB, and we don't have a kind of transitive equality as noted earlier. I mean, even if we did, even if we had a term here that said that C is equal to B, we'd have them separated by OR expressions. Or they'd be disjuncts, so we wouldn't have A equals C and C equals B. We'd have A equals C or C equals B. So we can't transitively apply that equality. The trick here actually, I think, would be to, we might be willing to, and this is kind of sleight of hand, but we might be willing to distribute that equality before, but no, that doesn't work. Here, we can distribute that equality on the basis of saying that the ordered pair AC. Well, we can say that A is equal to C. We probably are willing to say that A is equal to C at this juncture because we're saying the ordered pair is an element of the identity. But we still don't have anything for the ordered pair CB as an element of R. Even if we wanted to say that equality statements between variables are global or something, which we don't have a reason to say, that still wouldn't give us that C is equal to B. Unlike here in the second expression where we say, no, it's the same point here actually. df is equal to ii, so d is equal to f through some transitive equality sequence. Which means that we could replace this with d, but we can't replace e with d. No, but actually that's interesting. We can replace f with d. Similarly, this could be dj instead of ij, but we can replace f with d and then have the ordered pair de as an element of R. And then we would have the terms E equals the ordered pair DE, and the ordered pair DE is an element of R, which would give us that E is an element of R. I'm not sure that that's useful to do. A lemma strikes me. If I say if I say for all A not the ordered pair, well actually we need more quantifiers. For all A, for all B, and for all C, not the ordered pair AB is equal to the ordered pair AC. Actually, I'm not sure this butts up against I'm not sure this butts up against our definition of equality. We noted that we had effectively more than one definition of equality, but actually maybe we don't have more than one definition of equality. What do I mean? So when we're talking about ordered pairs, we are talking about sets. So we could try to use the same definition of set equality, though we've effectively sidestepped using the same definition of set equality. Let me think here. That was supposed to be red, but whatever. Okay, so if I say not for all D, if D is an element of the ordered pair AB, then D is an element of the ordered pair AC. And if D is an element of the ordered pair AC, then D is an element of the ordered pair AB. No, rather, this should be CC. D is an element of the ordered pair AB. Alright, now technically, though we don't get down to this technicality so often, but this is why we do axiomatic set theory instead of hand-waving set theory, I suppose. It's probably time to retire that pencil. Maybe a little bit more, but it's getting close, because... Anyway, interderivable with the expression... not for all D. D is equal to the is equal to the set containing its elements A. Yeah, well, we don't have that kind of expression. We don't use that kind of expression for the most part. But okay, D. Really, if we find ourselves drawing set symbols, set braces in a proof, we've probably gone wrong somewhere. But okay, D is equal to the ordered pair, or the set containing its elements A, or D is equal to the set containing its elements, the set containing its elements A, well, no, rather, the set containing its elements AB. Okay. Then D is equal to the set containing its elements C, or no, let's not close that parent. Okay, or D is equal to the set containing its elements CC. Probably could have taken that simplification step, but whatever. I like noting that that's a requisite step to collapse this and then collapse this. Which I will note here, and then I will note here. Right. And if D is equal to the set containing its elements C, or D is equal to the set containing its elements C, which I will once again collapse immediately. Then D is equal to the set containing its elements A, or D is equal to the set containing its elements AB. Okay. And we could go ahead and do the conditional equivalence, not just to skip a step, or and not or. Okay. So this is interderivable with the expression not. This quantifier should have been outside of that bracket, I think. not D is equal to the set containing its elements A, and not D is equal to the set containing its elements A, B. Or D is equal to the set containing its elements C. Okay. And not D is equal to the ordered pair. Rather, not D is equal to the set containing its elements C. Or D is equal to the set containing its elements A. Or D is equal to the set containing its elements A, B. Now, but this brings us back to that equality question. What do I mean when I say D is equal to the set containing its element C? Like, is that finally the equality of identity, or am I furthermore needing to state that? Well, we could go further. I mean, this is a set that contains elements. I could say for all E, we could do a little bit of a limit here. Let's see what we end up asserting. D is equal to the set containing its elements C if it is interderivable with the expression for all E. If E is an element of D, then E is an element of the set containing its elements C. And if E is an element of the set containing its element C, then E is an element of D. Okay, which is interderivable with the expression not E is an element of D or E equals C. Okay, well, we're back at the equality question, aren't we? Though now we don't have a way of breaking it down further. We might take a step back and say we didn't have a way of breaking it down further here, or that it's not useful to break it down any further, but... And not E equals C, or E is an element of D. Okay. And now, horrible logic. For whatever reason, I'm not foresighted today, so we'll just calculate. We have math so that we do not always have to think. Okay. not E is an element of D. That's capital D. And not E equals C, or E is an element of D. Okay. Or E equals C and not E equals C, or E is an element of D. Okay. Which is interderivable of the expression. Well, so this ends up being a contradiction. Not E is an element of D and E is an element of D. Surely not. And then this ends up being a contradiction. So we have not E is an element of D and not E equals C. Or E equals C and C is an element of D. Alright. Which we can further reduce. It's not, again, we're getting into the point where none of these reductions are doing anything for us, I think, but not E is an element of D and not E equals C, or E is an element of D. So I could distribute through again, and then this would form a tautology. And then we would have not E equals C, or E is an element of D. Which we could wrap up in a bow as saying that if E is equal to C, for all E, if E is equal to C, then E is an element of D, which is a suitably trivial, suitably boring expression to fall out of all of this. So what this supposedly gave us is that if we say that D is equal to the ordered pair, rather, if D is equal to the set containing element C as features up here, or really for any of these equality expressions, then for all E, if E is equal to C, then E is an element of D. That is not actually a satisfying, as it turns out, that is not a satisfying conclusion to reach for this equality sequence, because we would also want, we'd probably want to be able to say, Well, I don't know. I mean, it clearly falls out according to our rules for syntactical manipulation. Albeit we haven't checked these rules in a while. It's curious that this doesn't leave us with any terms expressing the idea that if E is not equal to C, then E is not an element of D. Though we did have such a term, we could say not E equals C or E is an element of D. No, it doesn't quite express it, I think. Yeah, I don't know. This is all. It's all turning to dust. It's all gibberish. Oh no. Noted Twitch mathematician asserts it's all gibberish. All of it. Every last word. Uh-oh. What are we saying up here with these quantifiers? An unrelated question. We say for all A, for all B, and for all C. If I'm saying for all C, not D equals the set containing C, or D equals the set containing Z. Yeah, what does it mean to say that for all A, D is equal to the set containing its elements A? Or am I misunderstanding my quantifiers? I think I'd have to be, wouldn't I? Well, these elements were distinguished from each other by their placement in ordered pairs. So we've destructured these expressions to the point where now it seems like this is a tautology. Like if these are universal quantifiers and there's no distinguishing characteristics. Well, actually, here is a distinguishing characteristic. D is equal to the set containing its elements A, B. We could continue through with the horrible logic. Did I say Twitter? I meant Twitch. Whatever, doesn't matter. Let's see. So if we make this the P term, the top line, and this Q or R or S, I guess, then let me see here. We'd have This ends up being really horrible. We could do this with letters though. So if this is not P, this is not Q, this is R, this is not R, this is P, and this is Q. Then we have not P and not Q or R, and not R or P or Q. Okay. Right. Let's get down to logic. Okay. Not R and not P and not Q or R or yeah, we could do these on 3 lines and do a cross. Alright, and then we'll have P and not P and not Q or R. Okay, so this would be ORed on, and this would be ORed on as well, and we'll have Q and not P and not Q or R. Alright, so this term is interderivable. Expression is interderivable with so this turns into a contradiction. Actually, yeah, we get easy contradictions here. So this turns into a contradiction, this turns into a contradiction, and this turns into a contradiction. Okay, so this will be not P and not Q and not R. And then it'll be or P and R, or Q and R. Okay. I need a keener eye for whether something can be reduced or not. I don't know if an additional step would constitute a further reduction. Like if I distribute this P and R through. I'm guessing not. Alright, so not P, not D is equal to the set containing its elements A, and not D is equal to the set containing its elements A, B, and not D is equal to the set containing its elements C, or D is equal to the set containing its elements A, and D is equal to the set containing its elements C. Or D is equal to the set containing its elements A, B, and D is equal to the set containing C. So we could further deconstruct these terms. If not D is equal to the ordered pair, rather, if not D is equal to the set containing its elements A, I guess if for all E, if E is an element of D, if E is an element of D, then not. I don't know. Or again, we go back up here and we have these terms. This kind of, we should close this lemma. Whatever we want our equality to mean, we probably want to be able to say here, let's store this term for now. We probably want to be able to say that if D is equal to the set containing its elements A and D is equal to the set containing its elements C, then A equals C. So actually, maybe this would be step down. And then I guess we'd want out of this that A equals C and B equals C, in which case A equals B equals C. Meaningless gibberish lurking just beneath the surface. Hmm. This line makes me think that set membership is always a positive characteristic, which is to say that until stated otherwise, every set is empty. And then sets only contain as elements what we attribute to them. If this, well, it's so to say, if this is derivable from asserting that D is equal to the set containing as element C, then yeah. So if for all E, if E is equal to C, then E is an element of D. Okay, and this doesn't have an additional term that says, and for all F, if F is not equal to C, then not F is an element of D. So either this is defective, either this demonstrates some kind of defectivity, some kind of defect, or set membership is positive. Positive. Yeah, what was the dispute that this is trying to resolve? Unclear. Alright, I'm gonna take a break. I'll be right back. I'll leave this substantially more impressive bit of hand waving on screen. Okay, I guess I'll check chat for the inevitable spam bot that I will have to delete. Yeah. Okay. Well, we can take another step without worrying about this for the moment. Mhm. Okay. Now, this needs to be extended. Alright, so if I have okay, and we will mark these with 2 colors as well. Alright, so this will break down into this term and gray. Or this term and whatever color this is. Blue green, aqua green, whatever. Or and here, and then all right, and now the idea is that each of these terms is in turn yeah, I gave myself too little room for no good reason, but whatever. So we did the same trick last time. So this will now be P and Q or R. Okay, so this is not E is equal to the ordered pair AB, so for all. And then this is an assertion that there exists. Okay, so now if I distribute through, this gray term will be in contradiction with the blue term. And this term should be in contradiction with let me think here. Yeah, we actually don't get the easy contradiction like we did before, like we thought we did before anyway. We get the easy contradiction here because these are assertions about E. Maybe we do still get the easy contradiction. I'll have to think about it. Let's see, so we have this term, we'll ignore that for now. I want to look at black. So, yeah, this will be a contradiction. E is an element of R and not E is an element of R. Okay. Now what about the other terms? There exists an F and there exists an E such that the ordered pair Fe is an element of R, or as opposed to for all A, for all B, and for all C, not the ordered pair CB is an element of R. Okay, so that should be a contradiction. That sounds like a contradiction. Okay, so under turquoise we will also have a contradiction. Now the question is, do we want to treat this like a contradiction? For all A, for all B, and for all C, and for all G, the ordered pair AC, not the ordered pair AC, is equal to the ordered pair. Let me think. Well, we can always ask first, what do we get if we treat that as a contradiction? Okay, so what remains is indigo and gray. Or indigo and turquoise, or whatever this is, or indigo and here, or let me note that this is under dispute. Okay, and black. All right. Interderivable with the expression not E is an element of R, and not E is equal to the ordered pair AB. Okay. Or that one's going to need its own line. I think the trick here was that we and down this term anyway, so writing it out is a little bit pointless, but not there exists a G such that the ordered pair AC is equal to the ordered pair G, and there exists an H such that the ordered pair GH is an element of R. Okay, or and here we bring back in there exists a P, and there exists a Q such that D is equal to the ordered pair PQ. Or not D is an element of R. Okay. And now the fabulous trick. Let's distribute some quantifiers here. So for all A and for all B, and for all C, I suppose. Okay, and then here, and then here, and then here. So the fabulous trick we pulled off was that we and down this term, we and down this term, and we and down maybe this term as well. Certainly we and down these two terms, and that leaves us with not E is an element of R, or not E is an element of R, or not E is an element of R, and, or maybe all three of these are not E is an element of R. And then we have or E is an element of R and. Okay, and the point of this is that this expression is there exists a D and there exists an E, such that E is equal to the ordered pair DE. So I guess we'd also and down this term. And at the end of all of that, we get, and we and down that term, E is an element of R, okay? And at the end of that, we get not E is an element of R, or there exists D and there exists an E such that E is equal to the ordered pair DE, which is pattern matched against this expression. However, that's also only forward derivable. Or do we only need forward derivability? No. Interderivability? Are we sure about that? Yes. And what we wanted to get out of this was right, well, I mean, we can let me think here. So we have not D as an element of R. And the trick we tried to pull, though now I'm thinking it was not legitimate, is that if we're saying for all D, not D is an element of R, then we could say not the ordered pair. Not the ordered pair CB is an element of R. Okay, so the idea would be that this term by itself is interderivable with the term not D is an element of R and not the ordered pair CB is an element of R. And with that term, we can OR on everything else. Disjunction introduction. However, we still have this hanger-on term, there exists a P and there exists a Q such that D is equal to the ordered pair PQ. We can go back and apply some thinking to this. And what thinking is there to apply to this? Why would this be questionable? So we're claiming that this is in contradiction to this term. So altogether we would be saying for all A, for all B, and for all C, though only for all A and for all C here. Not there exists a G such that the ordered pair AC is equal to the ordered pair GG, and there exists an H such that the ordered pair GH is an element of R. As opposed to there exists a D and there exists an F such that there exists an I such that the ordered pair Yeah, I mean, I think maybe we can see why it's difficult to accept that as a contradiction, because it's not clear what the actual contradiction is. I mean, in point of form, they're contradictions, but are they given the quantifications we have? I don't know how to settle that question. Not there exists a G such that the ordered pair AC is equal to the ordered pair GG. For all A and for all C, not there exists a G. So then not there exists. Yeah, I guess the contradictions may be more obvious if we re-extract the negation outside of these quantifiers. Not there exists an A, not open bracket, there exists an A, there exists a C. I mean, we could work the distribution through. Nah, it's not going to work the way I'm wanting it to. This blue term. No, yeah, this blue term contains the expression E is equal to the ordered pair DE. Okay, but that, yeah, never mind. That doesn't work. There's not going to be a way to rewrite this ordered pair in terms of D and E, because there's not going to be a conjunction of if we had this term and blue, we're not going to get a rewrite. We're not going to have E is equal to the ordered pair DE and E is equal to something else, because this term doesn't have that expression, or that term rather. It doesn't have any term that says E is equal to some ordered pair. I think we should be able to. I think we should be willing to accept this as a contradiction. We'd be saying for all A, for all C, not there exists a G. Such that AC is equal to the ordered pair GG. And this is an instance of for all. I mean, D and F are such instances that we're claiming exist, but they don't exist. Okay, we can accept that, but then that still doesn't resolve the difficulty. We can perform the anding down required to get the left-hand side, but we can't do the ORing on because of this term. We can't do the ORing on to get this expression back. And then what remains is to ask whether there's some horrible logic we could perform that would give us this as a base. Because we can only get there with this disjunction. I mean, we'd have to OR something on where D equals, there exists a P and there exists a Q such that D is equal to the ordered pair PQ, or something gives us, for instance, this term. Or, like we'd have to be able to combine this term into some other expression to yield one of these terms. Then we suppose we can take this term, not D as an element of R, and derive not D as an element of R and not the ordered pair CB as an element of R. and then or on everything else. Hmm. A stumper. I don't know what to do with this. Hmm. Perfectly legitimate operation here that we could perform. We could or duplicate D is equal to the ordered pair PQ and then and on a tautology. Alright, so then we get D is equal to the ordered pair PQ and D is an element of R, or D is equal to the ordered pair PQ and not D is an element of R, or the original expression. Okay. Intriguing, yeah. Let's see. Is this doing anything? So we can and down this. Well, having already accepted that we can perform this anding down operation, we can do a bunch of anding downs here to get back to the left-hand side. So, in our desperation, this doesn't seem like a legitimate operation. It seems like I've cheated here. But maybe not. Alright, so this would be forward derivable with... yeah, we did cheat. Yeah, you can't do that. System error. You can't and on a contradiction, you can and on a tautology. Yeah, this is a tautology. Hold on. Okay, well... If it doesn't work, if it doesn't do anything, then we don't have to care whether it's legal or not, I guess. Let's see. So now we're going to get D is equal to the ordered pair PQ, and D is an element of R. And then the idea is that we're also going to OR this down. Oh, well, yeah, we can do that in 2 steps. Or D is equal to the ordered pair PQ, or D is equal to the ordered pair PQ, or not D is an element of R. And so now we're going to OR delete here. Okay. Which will be interderivable with the expression D is equal to the order pair PQ, and D is an element of R, or D is equal to the ordered pair PQ, or not D is an element of R. Let me formalize that a little bit further. I feel like that can't be legal and that we've done something wrong. Okay, so if we say P or Q. Okay, we'll take this in 2 steps. So P or Q is interderivable with P or Q or Q, which is interderivable with P or Q or this step might be strictly unnecessary. Okay, let's see. Q and R or not R. Which is a tautology. Yeah. And then P or Q or Q and R. Yeah, we did cheat. Or Q. No, yeah. Q and not R. No, because this is all still or-wise associative. And now we step down the not R. Or whichever of these two we want to step down. Mm-hmm. That should be forward derivable. No, it shouldn't be forward. Why not? Well, so it is. Yeah, okay, let's see. Sure, that's forward derivable because we step down here. However, if we start with, so that's, I guess, part 1 of the proof. However, if we start with P or Q and R, and then we step down the R, then we get P or Q or Q, and then we or eliminate, and we get P or Q, which is the other side of the proof. Which gives us P or Q is interderivable with P or Q or Q and R. All right, the rare appeal to a truth table. If we have P, Q, and R, and then we have P or Q, and then we have, sure, Q and R, and then we have P or Q. I think this is going to be legitimate. That's horrible. Is logic just completely meaningless then, or? Maybe. All right, so T F F. I mean, there might be some logic interpretation that makes this sound reasonable, but in terms of how we've been using logic purely as a substrate for calculation, this is meaningless gibberish. Okay, T F F T F F T F T F F P or Q, true, false, Q and R, true, false, true, and false. Incorrect. Truth tables, mysterious. How do they work? Let me see. This is wrong. That's correct. This is wrong. This is wrong. And this is correct. All right. So Q and R. False. And false. Okay. Yeah, well, I mean, so these are... Because these are ORed on, ORing on an additional term like that. Oh, well, this is just disjunct introduction. I mean, for that matter, we don't have to go through this entire step. We could just say P or Q and then OR this Q and R on however it pleases us. Maybe more importantly, this doesn't solve any of the problem we have because it doesn't get rid of this Q term. Huh. But okay, by default, we get T, 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 and T. And then this would only be true if Q was true to begin with. Any case where Q is false, this term is false. So T and T, and then F and F. Okay, we messed up the truth table in more than one way. This should also be true. And this should be false. Okay. And similarly, these will be false and false. But yeah, this is just disjunction elimination. You can do that anytime you want anyway. Not disjunction introduction. But then disjunction introduction is it's not truth value preserving. Because I could OR on not P and then not Q. Wait a minute. Wait, why do we allow ourselves disjunction introduction? Cracks in the foundations? I think maybe we've been violating something about not being we can introduce disjunctions but not of bound variables, something like this. Let me do a little bit of research. Disjunction introduction, also known as addition, is a rule of inference in propositional logic that allows you to add a disjunction, an or statement, to a true statement. If you know that P is true, you can conclude that P or Q is true, regardless of the truth value of Q. Huh. So it's true that it's not truth value preserving unless you already know that the statement is true. But then actually, maybe the point here is that our appeal to truth tables is not useful because we don't assign truth values to these terms. All of these terms are presumed to be true. I guess which defaults us into the case that we can add a disjunction anytime we want. So the appeal to a truth table might have been spurious. Bizarre. Okay, does this do anything for us? No. Because we still have this term and we can't get rid of it. We could skip. We don't do that often. Some might say we don't do it often enough. Why would this statement be true if we want to engage in a little bit of semantics? R is a relation, then the identity of the domain of R/R is equal to R. So I take the domain of R. Well, yeah, we could do a concrete example. I take R, it's an arbitrary collection of ordered pairs. I take the domain, and then I create the reflexive pairs. Let's do it. Let's claim our step down from right to left. So I say that R is equal to the set containing as elements the ordered pairs A, B, C, D, and for good measure, E, E. And for even better measure, the ordered pair B, A. Okay. Now, so CD will be the odd one out in one regard. EE will be the odd one out in another regard, and then, yeah, okay. So now we're going to have the identity of, let's see, the domain of R, rather. The domain of R is equal to the set containing its elements A, C, E, and B. Okay. The identity of the domain of R is equal to the set containing its elements, the ordered pairs A, C, C, E, E, and B, B. Okay. And now I don't really know how to do the next step. I don't really know how to do it. Oh. I've never written an example out for slash. I really don't know what that operation does. I just know how to work with it in proofs. Let's see. Well, we should still be able to do something concrete here. So if we say A slash B is, we'll say for all D, for all D, D is an element of A slash B, is interderivable with the expression. There exists a P, there exists a Q, and there exists an R, such that the ordered pair D is equal to the ordered pair PQ, and the ordered pair PR is an element of A, and the ordered pair RQ is an element of B. Alright. And now to do some pattern matching. For all E, sure, E is an element of the identity of the domain of R slash R is interderivable with the expression there exists a P, and there exists an S, a T, and a U. Sure, there exists an S, there exists a T, and there exists a U, such that D is equal to the ordered pair ST, and the ordered pair SU is an element of the identity of the domain of R, and the ordered pair UT is an element of R. Okay. So this would be D is equal to the ordered pair ST, and the ordered pair SU is an element, well, the ordered pair SU is equal to the ordered pair AA, or the ordered pair SU is equal to the ordered pair BB, or the ordered pair SU is equal to the ordered pair CC. Guess I should have done this on a new line. Or the ordered pair SU is equal to the ordered pair EE. Okay. And the ordered pair UT is equal to an element of R, which we have specified is is equal to the ordered pair AB, or the ordered pair UT is equal to CD, the ordered pair CD, or the ordered pair UT is equal. I'm actually going to run out of room. I haven't had the entire line. Yeah, oh well. Ordered pair UT is equal to the ordered pair EE, or the ordered pair UT is equal to the ordered pair BA. Okay. That ends up being horrible. I wonder if... Yeah, I should probably look up a set calculator. I don't think I would use it actively, but I don't want to calculate... I specifically don't want to calculate this. Though each of these expressions breaks down. So D is equal to the ordered pair ST, and S equals A. So each of these is going to be... let me think here. S equals A and U equals A, S equals B and U equals B. This is gonna be horrible, but whatever. It's free content. Endless free content. Look at it. Let's see. Okay. Now, what happens here? Okay, so actually, let's use Poppy Red. Okay. That was not the point of using Poppy Red, yeah, but still doable. All right. Okay. And then so distribution here, P and Q or R or S or T. Okay. Right, we decided not to scrub for several reasons. At least 2 reasons. Let's see, so P and Q, and then this in turn gets distributed back. Okay, which means that we're going to have red and okay, I'm not sure that left enough room actually. All right. Be a little bit uneven. Garbage collector. Should we need black? All right, now. Oh, and then here. No cancellations either. Nope. bracket, 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 bracket. Incorrect. Oh no. Let's see. All right. Now, what are the connectives here? P and Q or R or S or T. Okay. So between all of these will be or. Okay, between lines, and then between entries. Between entries, we will have P and Q or. So ands. So these brackets were unnecessary because this is all going to be or wise associative anyway. Alright, and then between these ors. Okay. And now we might not work through all of this. We might just get a sample here. So S equals A, or you just might do the whole thing, I don't know. And U equals A, and U equals A, and T equals B. Okay, that's one term. Or, yeah, that's, we're gonna have a bunch of empty space over here, because I can't fit two on a line, unfortunately. Let's see. And then we'll have, so this is all going to be the same. S equals A and U equals A. Okay, bracket, bracket, or, and, U equals C, and T equals D, bracket, U equals E, and T equals E, U equals B, and T equals A. Okay. From which we may derive that the ordered pair ST is equal to the ordered pair AB. From which we may derive Alright, so AD AE, and then AA. continuing for a moment here. Which is in turn equal to D. Because D equals the ordered pair ST would and distribute. Okay, but this presents the immediate and seemingly incontrovertible problem that what are we doing here? Hold on. Let me see. Need to follow through on the chain of logic. It seems like we've disproved this assertion. Why? Well, I don't know how to take these forward derivability assertions. If these, on interpretation, if these are saying that the ordered pair AB is an element of R, the ordered pair AD is an element of R, the ordered pair AE is an element of R, and the ordered pair AA is an element of R. None of those are elements of R. Well, actually AB is an element of R, but none of the others are elements of R. Which presents a problem, because the whole point of this proof was the identity of the domain of R/R is equal to R. So if our construction is correct, and if that's the assertion being made here, then we have a counterexample to this theorem. Okay, let's see. Is there a prize? Can we get published? R is equal to the ordered pair AB. Okay, CD, EE, and BA. The domain of R is the set containing its elements A, C, E, and B. The identity of the domain of R is equal to the ordered pairs AA, CC, EE, and BB, the set containing those. Okay, and now we say for all E is an element of the set containing as elements. Rather, E is an element of the identity of the domain of R/R is interderivable with the expression there exists an S, there exists a T, and there exists a U, such that D is equal to the ordered pair ST, and the ordered pair SU is an element of the identity of the domain of R, and the ordered pair UT is an element of R. Okay. Now, the ordered pairs that are elements of the identity of the domain of R are specified here. They are AA, so the ordered pair SU is equal to AA, or the ordered pair SU is equal to BB, or the ordered pair SU is equal to CC, or the ordered pair SU is equal to EE. Okay. And when we say, let's see, and the ordered pair UT is an element of R. Okay, well that means the ordered pair UT is equal to the ordered pair AB, or the ordered pair UT is equal to the ordered pair CD, or the ordered pair UT is equal to the ordered pair EE, or the ordered pair UT is equal to the ordered pair BA. Okay. Now, that breaks down into saying, yeah, so this is the expression here. What time is it? Okay, we have a little bit of time. So I assume this is going to capture all of the elements, though we would have to do the next 3 lines to confirm that fact. We got AB out of this. What are we supposed to make out of this OR expression? The resulting OR expression. Let's, for the sake of charity, sure. I will grant that this generates all of the relevant elements alongside an ocean of irrelevant elements. Oh, well, okay, so there's a... Well, no, that doesn't help, does it? Because this is a constrained... This is a constrained assertion. If R is a relation, then... Yeah, but all that tells me is that every element of R is an ordered pair. So the idea would be now we have an expression that says D is equal to the ordered pair A, B, or dot dot dot, or D is equal to the ordered pair CD, or D is equal to the ordered pair, or dot dot dot. We're not gonna have whatever. Or dot dot dot, or D is equal to the ordered pair EE, or dot dot dot, or D is equal to the ordered pair BA. Or dot dot dot. Okay, and these statements would all be false. Okay, but I can OR on a contradiction anytime I want, and I can also negate them. So this would be interderivable with the expression D is equal to the ordered pair AB, or D is equal to the ordered pair CD, or D is equal to the ordered pair EE, or D is equal to the ordered pair Okay, and then we get and R is equal to the set containing its elements. The ordered pair AB, the ordered pair CD, the ordered pair EE, and the ordered pair BA. Okay. So no, I don't think we disproved this theorem. We do get a bunch of irrelevant elements, but they're contradictions. Well, what does it mean for them to be contradictions, though? Yeah, what do I mean when I say they're contradictions? No, I think this might be wrong. Well, okay, I guess this butts up against a rule. Let me. So. If I say what is our element of rule? What do I mean? Let me see. If I say for all f f is an element of R and R is equal to the set containing its elements A, B, and C. Then this is interderivable with the expression f is equal to A, or f is equal to B, or f is equal to C, and R is equal to the set containing its elements A, B, and C, which is forward derivable with the expression f is equal to A, or f is equal to B, or f is equal to C. What this is producing Yeah, so well, this whole sequence is saying for all E, if E is an element of this set, then E is one of these, or it's something that it's either one of these elements or it's something that shows up in this. Yeah, it's something that shows up in this sequence. Okay. The identity of the domain of R/R. Okay, so seemingly, I'm not. We'll have to look at this again tomorrow, I think. Seemingly, what this has shown is let's see. Forward derivable, though that's also going to get a comment. The identity of the domain of R is equal to the set containing as elements the ordered pair A, B, ... the ordered pair C, D. So it is going to contain all of the relevant elements. ... the ordered pair E, E. ... the ordered pair B, A. ... Okay, which is not equal to the set containing as elements the ordered pair A, B, ordered pair C, D, ordered pair E, E, and the ordered pair B, A, without the ... So what we would actually have is that R is a subset of the identity of the domain of R. Huh. Alright, well, we'll find out tomorrow, I guess. Look at it more. For all E, E is an element of the identity of the domain of R if and only if we switched over. Yeah, we could just change that at the top to D. D is an element of the identity of the domain of R/R is interderivable with the expression which is interderivable with the expression in this case. So, I mean, we're presenting a counterexample, so interderivable with this expression did we do the logic wrong? Let's see. We distribute through and we have P and Q. And then we distribute back through and we have P and Q, or P and R, or P and S, or P and T, which is what we have here. When we distribute through, we have P and Q, or P and R, or. So S is equal to A, and U is equal to A, and U is equal to A, and T is equal to B. Or S is equal to A, and U is equal to A, and U is equal to C. And T is equal to D, which is our first example of an incorrect element. The gap here is that the gap here is reintroducing the assertion that this is about these elements being in this set. Or the gap is taking this step from saying, the step from having this OR chain to saying that this whole thing is the assertion that each of these elements is an element of the set. Alright, we'll think more about that tomorrow.